frequently when I talk to people, they'll say, "Hey, come in. I want to talk to you about domain customization for entity extraction," and I'll be like, "Great, love to. Let me get in there. Love to talk to you about it." And then on occasion, I get the call about, "Hey, we'd love to have you come in and talk about events." And I'd be like, "Okay, what's an event to you guys?" It's one of the hottest topics right now. It's got a lot of interest and energy around it. It's also, because of the variety and ambiguity, one of the most challenging aspects of NLP. And we've been working very hard for the last 2 years on delivering event detection. That's part of the pieces that we're going to be delivering with that Adaptation Studio product. And we have today with us Philip Blair, who's our senior research engineer at Basis. He's in the R&D team. So this is kind of deep in the bowels of investigative research. And he's been on the bleeding edge of what we've learned about event detection, what works, what doesn't, and he's going to share that with us today. Philip's got a master's degree in computer science from Northwestern University. He is a long distance runner. Good for you, Philip. It's a good pandemic exercise, long distance running. And he is currently enjoying his runs in Paris. So Basis, as a planetary or global entity, has people all over the world, and Philip has in our virtual environment chosen to work from Paris, which I think is a pretty smart move, Philip. Thanks. So with that, why don't you go ahead and take it away?
Yeah, thanks. And yeah, you can. Oh. Okay. Okay, thank you. So hello, everyone. My name is Philip Blair. I'm a senior research engineer at Basis Technology. And today we're going to be discussing events. So specifically, I'm going to give an overview of the problem, discuss why it might be relevant to some of you, describe what we've done so far at Basis to try to solve it, and then finally give a little bit of a sneak peek of what's going to be coming next. So what is event extraction? At a high level, it's the process of detecting events that are described by a piece of text. Now, the exact terminology varies widely across literature, but generally speaking, we try to distinguish between the abstract notion of an event, which in this example shown on screen would be just the phone call that's being described by this sentence, and the concrete roles that are part of that event. So, in this case, you'd have John, Susan, last Tuesday. These are pieces of that event that actually manifest in the text that we're identifying. And lastly, we find that typically events are associated strongly with various key phrases, or sometimes called trigger phrases, which are very strong signals that an event is present in a piece of text. So in this case, we have the word called would be one of these. So what makes this a challenge? You can take a look at this diagram illustrating the hierarchy of complexity of various HLT tasks. And as we move up this pyramid, we find tasks that are more sophisticated and, for an end user, probably more directly applicable to what they're interested in doing. For example, an end user might be more interested in named entities than the morphemes of the tokens in a document. However, as we move up this pyramid, each new layer requires reasoning about the layers beneath it. So for example, for named entity recognition, you need to look at the sequence of tokens in a document and say, okay, well, we think that these specific tokens represent a person, or these specific ones represent an organization, and so on. Similarly, for events and relationship extraction, which is a very closely related task, you have to reason about how are the named entities in this document utilized? What are they trying to express in terms of how they relate to one another? And this extra layer of indirection that you add increases makes it more and more difficult to apply automated methods to these problems. And so that's why you see this dotted line toward the middle of the pyramid, where everything beneath it, we can be reasonably confident that we can just throw it at a computer and the computer is going to give us a generally correct answer. I'm not trying to say that named entity recognition is a solved problem, but generally speaking, we can get decent results with pretty high confidence. However, things like event extraction and relationship extraction are still on this other side of the line where we really require more of a human analyst touch to figure out how these are present in text. And so what we are trying to do is try to push this line up a little bit and improve the capacity of our algorithms to extract these events. Now, a naive solution to the problem would simply do like a keyword search for these key phrases in your large corpus of text. So for phone calls, you might just look for the word call, right? Or various inflections of that word. However, you would find that, especially in a big data set scenario, you would generate way too many false positives with this approach. And the reason is that you need a system, for a production-ready system, you need something that can actually look at how these words are used in context and understand the sense that this word is being used in. And so this fuzzy reasoning requirement necessitates a machine learning-based approach to this problem. And so to motivate a little more why this might be interesting for this specific audience, we can draw a link between event detection and detecting disinformation at scale. So fake news is a rather broad term, but so we need to be pretty specific about what exactly we want to focus in on here. And so all of these forms of fake news can be harmful in their own ways. We specifically want to focus in on this last bullet point here, where the substantive information in the article is just factually inaccurate. There's no spin that's being misconstrued in a certain way. It's just totally false. And this happens. So we can look at this less discussed group called secondary infection by the journalists which uncovered it. Which has applied these tactics in real life. Now, this group's one claim to semi-fame actually was not disinformation based. They're the ones who leaked the details of the US-UK post-Brexit trade agreement right before the UK had their general election back in 2019. However, they did fail at a number of disinformation campaigns over a period of about 7 years. And they all took a pretty similar approach, where what they would do is they would fake a document, sometimes very poorly, and they would then take this document and post it online alongside some news article or blog post or whatever, where they're saying, oh, look at this leaked document, which is revealing this bombshell news story that's just totally false. So we have a few examples here that we can look at. You see that the first two are targeting the Ukraine. On the left, we have a falsified memo from the US Senate accusing the Ukraine of ethnic cleansing. In the middle, we have a falsified memo from a Japanese ambassador, which is proposing that they nominate a Ukrainian politician for UN Secretary General. And on the right, we have a fake letter from the far-right Rassemblement National party in France, sent to the far-right Sweden Democrats party. All of these are fake. But they're all posted by this group. Now, we know that these are forgeries that were released on the internet, but in real life, we don't know this until after the fact. And so what we want to know is how can we utilize event extraction to develop a system which can help us detect these in real time. And so I'm going to discuss one potential solution to this problem, which is taken from a research paper published in 2019. And so, you could certainly adapt this into a production system, but it's really meant to just illustrate the idea of how event detection could play a role in a larger disinformation tracking system. So we have a challenge. Fake news is presented as unstructured text. Here we have this fake document, and there was presumably some sort of news article attached to it. And the problem is that if you're just trying to broadly track these disinformation campaigns, there's not a universal natural choice for a schema of how to categorize all of these unstructured documents. However, suppose instead that we have an event extraction system. We can then take this document and its associated post of whatever it was, run it through our event extraction system, and get structured output like what we have on the right here, where all of that information has been digested into the US Senate is accusing Ukraine of plans for ethnic cleansing. And there may be other events in there as well, but the point is that we end up with something that's nice and structured. And this is something that we can do on all of these documents and end up with going from all of this large unstructured corpora, all of this large unstructured data into some nice structured items that we can process. And we can start asking questions from here, such as how can we intelligently utilize these structures? And so a first step for how we can, for what we can do with this information is try to enrich it a little bit. So disinformation campaigns transcend borders. They try to influence public opinion across a variety of different groups in different countries. And so it's important that a real production system would be able to adapt to multilingual data. And so an example of how we could do this is users of event extraction systems will be familiar with the idea of linking entities to a knowledge base. So here you would have the context in which Rassemblement National and Démocrates de Suède appeared in the original document, and those would be linked to these concrete knowledge base identifiers that just universally represent the notion of the French party and the Swedish party. Then for roles which are associated with more free-form text, you could at least do some sort of language identification on that in order to facilitate later downstream cross-lingual semantic comparisons using things like multilingual word embeddings or things like that. And so once you've enriched the structure with this information, you could then potentially have an article written in French about this supposed incident and an article written in English about this supposed incident, and be able to connect the dots that these two articles are talking about the same thing. They're both talking about the same party, giving the same type of support. So now we can look at how the full system is going to look. The authors present a basic idea. Suppose we have a list of authoritative news sources. And I do want to note here that authority doesn't necessarily refer to any sort of editorial slant. It's strictly referring to the fact that, for example, the Associated Press is not going to say that country X bombed country Y when it didn't happen. So what we're trying to identify here is a list of sources which are going to give us a stream of events that we can be reasonably certain actually transpired. And I've listed mainstream news sources here, but conceivably this could be anything such as intelligence reports or anything else. Now, if we run our event extraction system on this database of legitimate articles, we then end up with a database of legitimate events. And so this is kind of our ground truth that we are trying to compare against. And what are we comparing? Well, we can take our data that's coming in from things like social media, things like blog post linked by social media, email forwards from your grandmother, whatever you want to check. You can run all of that through your event extractor and end up with a list of candidate events that we want to audit for their veracity. So we have our list of our set of legitimate events, our set of shared events. How are we going to determine which of these are fake? Well, since everything is nice and structured, we can actually compare different events to one another and cluster them together. And we end up with something like this, where you have events which are legitimate, and you have things that people who have shared those events on social media appearing very close to those legitimate events. And you can say, okay, well, these are just actual discourse about these real events, and that's totally fine. But then, on the other hand, you might end up with something like what you see on the right, where you have these events which were not clustered together with anything else, and so potentially these are fake news events. However, are they all fake? Probably not. If you were trying to scale this into a real system, one challenge you would find is that it is susceptible to false positives. Because conceivably, you could have an event which transpired but just hasn't been picked up by your authoritative news source yet. And so because of that, a real system here would need to track additional information, such as where these news articles are coming from. And then you can start connecting dots such as, okay, well, this news article talks about something that I can't find a cross-reference for, and it has this weird artificial sharing pattern. I think that's probably something that we need to escalate up to an analyst. And so since all of this hinges upon an event extraction system, I think it would be fitting for us to discuss our progress on making one in our research lab. And so while we've already mentioned that event extraction is a difficult problem, there's actually an additional acute practical issue that we at Basis run into as just a general HLT NLP software vendor, where traditional statistical algorithms for extracting a given event require a lot of training data, but because we're trying to produce general software, the list of events that different customers are going to be interested in is going to vary extremely widely. Even just among a set of intelligence community customers, you would have very different needs from different organizations. And so that presents a really challenging practical issue for us, because now we have to collect these large data sets for all of these individual niche use cases, which becomes a really nasty combination for us. So one thing that we wanted to solve right out the gate was, how can we reduce the amount of data that's required for event extraction systems? And our approach to this problem revolves around a concept from machine learning known as instance-based learning. And so traditional machine learning, the way it works is you're essentially fitting a statistical distribution based on your data. And this requires a decent amount of data points in order to accurately do. However, with instance-based learning, instead of actually learning anything and fitting a distribution, what you're going to do is just keep track of all of your training data set. And then whenever you get a new input, you're just going to go through that list and say, okay, which one of these training data points is my input most similar to? So you can see an illustration of this on the left, where we have this gray dot that needs to be classified, and we see it's closer to the orange. So we're going to say, okay, we're going to copy over the label from that orange data point. So what's really great about this is that you can start classifying things with as little as one data point, because you can just threshold that similarity and say, okay, if it's within a certain distance, we'll copy the label. Otherwise, we'll say that there's no event here. But on the downside, you're iterating through all of your training data every time. which means that as your training data set grows, this starts to scale really poorly. And additionally, when you're dealing with these high dimensional problems like event extraction, in order to really exhaustively enumerate everything in order to prevent recall issues, you need to have an extremely large amount of training data for something like this. However, this is good for bootstrapping, and we have, as we'll see in a moment, we have successfully applied this to real-world data. And I don't want to get into all the details of how the algorithm specifically functions here for events, but this is kind of the basic idea for what we're doing. We're going to take our input and all of our training data points, broadly segment them into different chunks of entities, key phrases, and everything else. And then we're going to try to run an alignment on those sequences. And our similarity metric that we're using for this instance-based learning is essentially how good of an alignment this ends up being. And then when we want to do our actual role extraction, finding the roles associated with this call event, all we're going to do is look at that aligned sequence and say, okay, well, Lisa lines up with the chunk for John, so we're going to copy the caller label here. Mark and Susan line up, so we're going to copy that label here, and so on. Yes, and so this algorithm has been successfully applied to real-world data. We worked with a customer who was interested in Japanese event extraction. They had a few different events in mind. A few different event types in mind, and one of which was arrests. So here on the top, I've just made up a sentence which illustrates what exactly they were interested in, with a translation on the bottom for those of you who don't speak Japanese. And you can see it's a pretty standard event type where it has two specific roles of arrestee, the one who got arrested, and arrestor, which was the one who did the arresting. And so when we did this work with this client, we collected both an English data set just for tuning the algorithm and a Japanese data set, which was what they were actually interested in. And so here are the results on this data. And so there's kind of a note about the evaluation here. It's a little special. Because we were doing this work in parallel with our work on active learning, we actually did not have a held out test data set to evaluate on. So instead, what we do is we evaluate using a technique called leave one out cross-validation. This is just a fancy way of saying we're going to evaluate on the training data, but we're going to not allow any of the training data points to match themselves. Because of course, if I query with the training data point and it finds the closest thing, well, it's a training data point, so it's going to be itself. And so you would trivially get like 100% accuracy, which we don't want. However, we do think that these numbers are relatively representative of how you would expect this algorithm to perform on a similar domain of data. Now, one thing you might notice is that the scores on Japanese are a bit reduced compared to English, and we have a few hypotheses as to why this might be the case. So first of all, for the recall, I think that the real story here is that English is a bit artificially high. I think this is because that first of all, the English data set was much smaller. So it's less statistically significant that you would see a 1.0 recall. But additionally, you have just qualitatively a less challenging data set than the Japanese data. So now for the precision, the issue here is that Japanese does contain more nuanced grammatical structures and more indirect ways of phrasing things that are commonly used in the types of data that we were working with. And that just seemed to be more challenging for the algorithm to deal with. A specific example was there was a sentence where someone was quoted as saying that the police intend to arrest people. And the way that that notion of intention is expressed in Japanese is just something that's somewhat specific, and the algorithm hadn't been exposed to that anywhere else. So it erroneously extracted it as an arrest event. Yep, and so what comes next at Basis? That's we were working on first improving this existing instance-based event extraction system. One thing that we found was the role extraction algorithm that we have at the moment is a bit too opaque. So because this event extraction schema contained no information about how roles should appear in text, this information just got totally inferred by the algorithm, right? You saw how that process of copying over the labels. We've since determined that it would improve the accuracy and give a bit better of a user experience if we actually expose this to users in a more fine-grained approach, where they can define things like regular expressions and what have you, to say that this role should fit this regular expression, things like that. And so this does introduce a little more overhead for adding new event types, but we think that the reduced data requirements and the accuracy boost are going to make it worthwhile. Similarly, we're playing around with some hashing tricks to try to reduce the amount of that training data space that we actually have to iterate through every time, just to try to help mitigate that scaling issue that we face with this algorithm. And finally, what's really coming next in the more medium to long-term future. In theory, there's going to be a point where we've collected enough data for a given event type that a statistical model is going to start performing better than our instance-based model. The reason being that the instance-based model just is not able to generalize as effectively as something statistically based would be able to. However, there's a couple of open questions here surrounding this, such as where exactly that point is where a statistical model would start outperforming our instance-based model. Because certainly at the beginning, the instance-based model does much better because it doesn't require very much data at all to start giving you reasonable predictions. And additionally, we want to know how much of an improvement should we expect to see with that statistical model. Of course, there's not going to be a universal answer here, but are we talking a few percentage points? Are we talking tens of percentage points? It's up for debate. But once we have the answers to these questions, we will be more than happy to share them with you all. And that's all I have for today. So thank you for your attention. I'd be more than happy to answer any questions about what we've covered today.
Fantastic, Philip. Thank you. Thank you so much. Appreciate it. Your presentations generated a healthy amount of questions, not surprisingly, around a couple topics that I'm going to ask you about. So big questions around the ability to generalize on the key phrase, right? So there's arrested and there is in custody. Is there a sweet spot right now or in the near future that would guide how many kinds of events are possible to detect, or some guidance on that?
So it's a good question. So the work that we've been doing so far has been around what you would typically call targeted event extraction, where you're going to, which I think this will answer the question, where you're going to essentially predefine the list of events that you're interested in extracting. So, you might say, I want to know about arrests, I want to know about phone calls, I want to know about someone traveling somewhere.
Right.
And then from there, you're going to start annotating data specifically looking for key phrases associated with those events. Now, our current algorithm is, it's not going to discover new key phrases for you. So that is going to be something that's part of the annotation process, where you need to actually seek out and find at least the set of key phrases that gives you good coverage over that event. However, automated key phrase detection is something that we'd be interested in supporting, especially once we have a statistical model for doing event extraction.
Gotcha. So that's where you see it kind of evolving over the next few quarters, months?
Yeah, like I think that that's kind of the ultimate goal, is for us to have something that is not so tightly coupled with the specific data that was annotated, and something that can kind of generalize a bit better on its own.
Right.
However, we do try to do some tricks to help mitigate the issue. Like, for example, the way that we look for key phrases is using lemmas, which, for those of you who aren't familiar, like arrest and arrested would both be the same from our key phrase extractor's perspective. So you don't have to, totally exhaustively list every possible way that you could phrase a key phrase.
Yep.
But it's still a bit of it's a bottleneck in the process for now.
Right. Thanks. There's a lot of questions. So probably the next section, if we touch about just quickly, is events are typically one step in a larger process. So if we take the example of fake news, right? The information that you laid out earlier, we've got the first step, which is the entity extraction, even to the point where it's sophisticated to identity extractions to make it unique, then the event, and then the details around that event. How do you then at that point detect, is this fake news or is it actual news?
Yeah, the system that I was presenting was really talking about, was really just mostly to serve as illustrative of how this could work. I mean, ultimately what you would end up wanting to do is you would need to have plenty of heuristics built on top of the extracted events and your similarity comparison in order to determine, okay, well, which of these are noise and which of these are actual fake events.
Right.
I'm not sure if that answers the question, but
yeah, it does. I mean, fortunately or unfortunately, I've had the experience of working with our mission partners that are doing just that. And so typically it's the event detection and then looking at the semantic proximity of that event. And so if you see 5 instances of that event and 4 align with each other and one's an outlier, that typically is a categorizer for that piece, whether it's the one is a fake news event versus the other 4. So it really comes down to being able to semantically reference these things together. And so we're using the cross-lingual semantic vector space in order to compare those events in French, Arabic, and English. So a lot of this gets into being able to detect that event and then using an orchestration of NLP tools in order to enrich and make sense of that event. A lot of questions around this, Philip. So please, for attendees, we're happy to have more in-depth conversations around specific use cases. This is an area that is really up to a lot of investigative research, as well as delivering some practical solutions right now. So we're happy to engage and get connected and have our R&D guys talk to people that are in the middle of this. So Philip, congratulations for being in the middle of the tornado and steering our way clear. Thank you so much.